In the previous section, we used the 4-wire handshaking protocol when using multi-cycle FPGA math and analysis VIs. By the end of this module, you will be able to perform high-throughput math. In this section, we're going to be talking about the high-throughput math functions. So what you see on this slide is the high-throughput math palette. This is a palette that is within the FPGA math and analysis palette. The functions that you see on this palette you can use to achieve high FPGA fixed point math and analysis rates. So you can place these in single cycle time loops and use these to achieve very high throughput. So all these operations are supported inside the single cycle time loop. Notice that there's a divide function in here. So this is going to allow you to divide inside a single cycle time loop. Also, there's a number of operations on here that are not available in your basic numeric palette. So for example, you see that there's trigonomic and also logarithmic functions on here that you can access. So in this slide, we have an example of one of the high throughput math nodes. In this case, we're looking at the divide function. So if you use this one, notice that you can double click it and you get some configuration options. So notice that you can configure the fixed point configuration, as you can see in red, and also you can configure the throughput as well. So as you're changing things up and changing the fixed point configuration, that could also affect what kind of throughput you can get. So on this slide, we see that the high throughput math functions are kind of similar to the FPGA math and analysis functions that we talked about before. So here, we see that you can also configure it to execute outside a single cycle time loop or inside a single cycle time loop. So if you want to get higher throughput rates, you would want to execute this inside a single cycle time loop. And notice over here, you can also configure its throughput. So if you take a look at this particular example, notice that in red, you see a setting there for throughput. You can adjust that for different throughputs. So for example, on the slide, you see that it is set to 17 cycles per sample. And if you look at the bottom there, notice that there is a throughput of 17 cycles per sample, and the note that goes with it is that the latency is 18 cycles. So you can see that through this configuration, you can figure out what the throughput and latency is going to be depending on your settings. So notice that at the very bottom, you see a throughput of 4 cycles per sample. So let's say we had adjusted that setting and we changed it to 4 cycles per sample. Notice the note that comes along with it. At the bottom, the note says that this function has a 5-stage pipeline. So to achieve that throughput of 4 cycles per sample, there was an internal pipeline that was built into this, and that's how that throughput was achieved. On this slide here, we see another subpalette. So this is a palette that you'll find within the high throughput math palette. So this palette is called Basic Elements, and the nodes that you see here you can use to perform low-level FPGA operations. So you see that there's one for accumulating totals there. You can also delay signals with a discrete delay in case you need to line up signals and things like that. You can do some binary arithmetic, and for these low-level functions, a lot of times you might use this as a building block in a more complex algorithm. So you might not even need to use these at all. The last thing I want to talk about there is the DSP48 node. So to achieve higher performance, you can use the DSP48 node to directly control the dedicated DSP hardware on the FPGA. While this offers the higher performance, it also introduces significant design complexity and also ties the design to the specific FPGA target or chip. So that'll limit future algorithm portability. So for example, if you're using one of these DSP48E nodes, and you're trying to port it over to another FPGA target that doesn't have that exact same DSP slice, then it's not going to work. So in general, we see that there's a lot of different options for you for FPGA math and analysis. There's a numeric palette, there was the high throughput palette, and there's even things like the DSP slice. So just know that all these are at your disposal, and you can choose them as necessary. Now you can perform high throughput math. Next, we will describe resources for integrating third-party intellectual property.